Welcome to the video lecture. Today I am going to explain about single phase transformer, how to represent a physical model to a circuit model. So, transformer is a very important device in power systems. You want to analyze the entire system, power flow equations, whatever it may be. First of all, a physical model is converted to a circuit model. So, in this session we are how to represent a physical model to a circuit model. So, you already know this transformer is it have the two main parts. One is the magnetic core, another one is the winding. So, which is connected to the supply, that is called as primary winding, which is connected to the load, or otherwise we are connected to the system, that is called as the secondary winding, where it is developed the primary terminal voltage, secondary terminal voltage, maybe it is connected to the load here, terminal load voltage maybe. Okay, but how to represent this entire transformer into circuit model? This is the symbol of transformer. Why? Because transformer having the two windings. I am considering this is called as a step down transformer. That's why compared to the primary side turns, secondary turns and taken the very less, and this is called as a core representation. So, this is the circuit model. First of all, you want to understand the any machine. First of all, we have to consider for the ideal nature. Suppose it is a ideal transformer. Ideal transformer not having any loss component, there is no voltage drop because of maybe the primary winding, and it is a zero resistance winding, secondary also zero resistance winding. So, automatically ohmic losses are there is no ohmic losses, and also the primary coil, how much flux is set up, the entire flux is linked by the secondary coil. Similarly, the secondary coil, how much flux is developed by carrying load current, that is also linked by the primary winding. So, that is why there is any leakage flux. Because of the reason we do not know any and also it is a almost the reluctance of the core is also 0, it should be 0. Once the reluctance is 0, the permeability of the machine is transformer is infinite. So, there is no any the iron losses. So, in this connection, generally the transformer in the ideal case, suppose it is connected to the voltage V1 in the secondary side in terms of V2. So, develop the voltage, there is any drop here, E1, induced voltage is secondary side voltage called as the E2, E1 and E2. So, here ideal case V1 is equal to E1, similarly in secondary side V2 is equal to E2. But practically any transformer having maybe you are using the copper wire having, it offers some resistivity. Due to copper resistivity, any resistance of the winding is depends upon the length of that coil, and inversely proportional to area of the cross section. Less wire, less thickness wire having the high resistance, and it also the resistance of the machine more length is nothing but it offers more resistance. It is also resistivity of the material. Because of that reason, so one number of turns are there, it have some length, it also area of the cross section. So, that is why it offers some resistance. So, similarly the secondary winding also it offers some resistance. not only that, every coil in ferromagnetic materials we are used here, even though iron, the cold roll grain oriented silicon steel purpose of and also laminated core is used here, even though it offers the some iron losses. So it have the iron losses and it has the copper losses. So both iron loss and copper loss are involved. So but all these losses, how can you represent in a practical transformer? So in practical transformer, it offers resistance. So maybe for ideal condition, normal, this is the transformer N1 and N2. Because of that, initially we are considering only no load current, and also there is no loss component. At the time, we simply remember it draws, even the open circuit, the primary is carrying some current that is called as no load current, that is represented by some inductance that is called as. So reactance, the purpose of it is the magnetizing current. Magnetizing current is represented the this value. So simply it is called some Xm. So here the open circuit condition, this is called I naught, here called as suppose here I2 equal to 0, this is called as I2 dash, the secondary current with respect to primary, it is also 0. Generally it is called as a primary voltage. So this is happen when you applied some voltage V1. So under no load condition, I1 is equal to I0, under I1 is equal to I0. But this is the practical transformer, it offers iron losses. Iron losses depends upon the only voltage. Why? Because of the flux reversal it is developed, so frequency is constant. So in the terms remaining voltage is already constant. So that's why iron loss is treated as constant. The constant parameters we can represent it in shunt way. That's why this is the any losses component we can represent the circuit in the resistive mode. That's why this is called as working component. It is as RW. So entire this I naught is resolved into the two component, that is the IW and IM. So it is the circuit diagram only for you are considering for the iron losses, but actually the winding loss also consider. We are added some more parameters. Now we can add this. So once the secondary winding parameters also included, the entire this is the equivalent circuit, the transformer. Secondary also offers some resistance. This is called as R1, this is called as R2. Once it is connected to the load, some ZL. And how can you represent the practically any transformer? Entire the flux is not linked by the another coil. So some of the maybe you are taking here, this is the transformer. In this transformer, this is the one of the coil. So once it is excited, this supply here, this is the another coil. So once it is connected to the load, so here it pass the current is I2, here it pass the current is I1. Due to I1, it set up some flux lines according to right hand thumb rule, it set up the some of the flux lines. Under load you already studied this. This is called the normal magnetizing flux. So entire some of the flux lines are not linked to the secondary coil. So these flux lines not linked by the secondary coil, that is called, due to that one certain voltage drop is occur. Similarly in the secondary side also we are applying this maybe this is the flux lines. So here also some of the flux lines are not linked by the primary coil. Due to that one, secondary side also some of the voltage drop is occur. That entire voltage drop in the nature due to that stored energy and stored flux, that is represented reactive component, that is called as leakage reactance, that is denoted as the leakage reactance. This is called as X1 and this is called as X2. X2 is the component, it is actually certain voltage drop, that is called as a due to leakage reactance, that is called leakage reactance voltage drop. So this is called as the leakage reactance of the primary winding. We already know we are considering the both the ohmic iron losses, that is the no load circuit. So overally, for example, once you give the voltage in the primary side V1, immediately develop the voltage E1 here, induced voltage in the secondary side is called as E2. That voltage depends upon the number of turns of the both primary winding and secondary winding. So V1 causes the actually it is called as I1. That I1 is generally it is resolving to the two components I0. This is called as I2. This I2 value is represented in terms of primary is called as I2 dash. So how to calculate the I2 dash value here? So we know that any parameter, secondary parameter you want to transfer with respect to primary, we are using the trans ratio, that is the we know that value. So I2 by I2 dash, why? Because this is the secondary component, it is the primary component is equal to A. So from this equation A2 is equal to A I2 dash, A I2 dash, like this. This is the actually it is secondary current represented by the primary side, primary side. Finally, from this equation here I1 is equal to I0 plus I2 dash, all are phasor notations, and see here this is called as RW, this is called as working XM, this is called as IW, this is called as the IM. So here I0 is equal to, once again it is the combination of both IW plus J of IM. This is the value, this is the value. So we apply the, because of the reason resistance and leakage reactance, the voltage difference are occur, applied voltage and induced voltage. We apply the loop equation here, apply the loop equation, we can consider E1, for example at a particular instant it is taken as a minus and plus, and plus to minus, in plus to minus. So minus to plus we can consider as a positive, and plus to minus, what current is passing, I2 dash, or rather simply maybe I2 dash into R1 plus JX1 minus plus to minus E1 equal to 0. So here the difference of terminal voltage and induced voltage is equal to the I2 dash into R1 plus JX1. So another important point. Now the main problem of this is the transformer generally it is a both windings are electrically isolated or magnetically coupled, where any coupling circuit in the big circuit it is more complicated. So by analyzing is very difficult. So that's why according to power invariance the entire power is same. So that's why with respect to the distance ratio generally the power is entirely we have to convert it to the a single equivalent circuit. That is very useful to the analyze the system. So you want to analyze the equivalent circuit, so all the secondary parameters maybe are transferred to primary with respect primary, or rather all the primary parameters are converted to the with respect to secondary. So these are all used by this equation. So generally in the previous class I told already this A values depends upon the primary parameters by primary voltage by secondary voltage, or maybe we are called it as different notations. So like that, in terms of current, the secondary current by primary current. So by using ratio we can convert the all the parameters with respect to primary to secondary. Now coming to how can you write the equivalent circuit with respect to primary, So we know the already circuit diagram. This is called maybe so no load current parameters, and this is called as the secondary side parameter with respect to primary, and this is the circuit, all these notations. Finally it is connected here, ZL, R2, X2, R1 and X1. Now this is called as RW, XM. We already know this is called as a V1, the particular instant. So the terminal voltage of secondary is called as a V2. Induced voltage in the secondary winding is called as E2, and induced voltage in the primary side equal to E1. So these are the ratios by this is the value. My aim is to convert this entire the secondary side parameters into primary. So how to convert that? So we are using a simple way. For example, losses of the both machines, total loss, we are call it as total loss of the primary winding and secondary winding copper losses, we are call it as R1 square R1 plus I2 square R2, I1 square R1 plus I2 square R2. It may be called it as with respect to primary, we are call it as I1 square R01. So here R01 is the overall loss component of the winding loss component of the entire the transformer reference. So this is called as with respect to primary, we can write it that equation total primary winding copper losses, secondary winding copper loss equal to with respect to, suppose entire the terms we can write it like this, I1 square R01. So here from this equation we can simplify this, how to convert this R2 value into in terms of primary. I1 is taken as the common here, I1 square, that is called as R1 plus I2 square by I1 square R2, that equal to I1 square R01. Now these are the cancelled here. So we represented here R01 is equal to R1 plus, that is called, this term is called as a R2 dash. Here the term very important. Here suppose you can take the entire the transformer, it offers some loss. Suppose we are connecting a wattmeter in the primary side and measure the value, that is the active power is equal to I1 square R01 is equal to this entire the both windings copper losses. So you want to represent that one, the R2 is converted to the secondary side, that is denoted as R2 dash. Here R2 dash is equal to I2 square by 1, that means I2 by I1 whole square R1. Here I2 by I1 you know already, that is called as A, that's why it is called as A square R1. So A square times sorry this is called as R2. So the R2 value is multiplied with the A square times, we are getting the value is equal to the R2 dash, that is called as the R2 parameter of the secondary. You want to rewrite this in terms of primary, that value is equal to the A square R2. By using this we can I just have to write this enter the equivalent circuit. First of all, primary side parameter, these are the secondary side parameters, and we write it already shunt components. This is called as I0, this is called as IW, this is called as IM, XM and RW, this is called as R1, this is called as X1, this is called as R2 dash and X2 dash, and also load is also transferred this side, that is called as ZL dash. This is the term. So we are applying, this is called as V1, that is called as V2 dash, this is the circuit diagram. Now we can write it. How can you, what are the values by using this the previous equation. So like any secondary parameter, series parameters you want to transfer with respect to primary, we are using this formula a square r2. Like that the same are applied for the components x2 and any series component and x2 and xl. What are the shunt cover, what you want any passive parameters you want to transfer from secondary to primary, we are using this formula. Based on that, so here we can write it, what is the r2 dash value, r2 dash is equal to a square r2. Similarly, what is the x2 dash, x2 dash is equal to a square into actual x2, and zl dash is equal to a square into zl, a square into zl. So this is the equation. Now further simplification of this equivalent circuit, these are all series manner. So overall the circuit of both the resistance are added is common term, and x1 and x2 is added. Finally we can rewrite as this equation, this is the, yeah, maybe this is called as V2 dash, this is the V1, or maybe this is called R1 plus R2 dash, and this is called as x1 plus x2 dash. And the shunt parameters here we can take it like this, and this is called as I0, and xm, these are rewrite is like this, these are the components IW and IM. So maybe we are, it is connected to the load, that's why it is called as a ZL dash, that is called as a ZL. This is the equivalent circuit of the transformer with respect to primary, Similarly the same method you are applied, entire the equation, entire the transformer circuit is converted either in terms of secondary or in terms of primary also. So further for big power transmission lines, the power transformer, the no load current is compared to the full load current is very less. For other simplification, sometimes approximately the no load component is neglected. Why? Because in terms of 1000 amps, this is one is it is negligible. For for more simplicity, sometimes for power transformer these shunt parameters are neglected. At that time the equivalent circuit of the transformer is simply, it is called as V1 and V2 dash. So this is called as a R01, this is called as a X01, where R01 is equal to R1 plus R2 dash, and X01 is equal to X1 plus X2 dash. So this is the circuit diagram. So some other sometimes very transformer, when the transformer size is increased, the resistance is decreased, so that's why only the reactance also represented. So this is the way complete the physical model of the transformer we can convert it. Actually it is a transformer that the main problem is the both windings are electrically isolated and magnetically coupled. So that's why for representation of transformer depends upon their internal parameters. So windings are offered to their internal resistance. Due to flux leakage, certain voltage will be dropped, that's why we are coming to the XL value. And also iron losses, this is the iron loss component, this is the magnetizing current component. These are all represented in the form. Now it is converted, this is the equivalent circuit of the transformer. So for other simplicity, entire the by using the power invariancy, all the secondary parameters are converted to the with respect to primary, or all parameters are transferred to the with respect to secondary. Now form a simple equivalent circuit. So now we replace the transformer and provide the circuit and easily analyze the any electrical system. Thank you.